Hello, my name is Dhairya and I will be giving a presentation on flip-flop based memory for adaptive headlight systems. Adaptive headlight systems are an advanced vehicle lighting systems which are designed to automatically adjust to the direction, range, and intensity of the headlight beams based on real-time driving conditions. Why you may ask this is important? Because they store real-time sensor data, retaining system states, enabling fast and responsive decision making, which helps the driver focus on driving more than the adjusting the headlights and prevents accidents. Basics of flip-flops. The flip-flops can be considered as feedback loops with logic gates. They will hold a value until a new input triggers that change. There are various types of flip-flops: SR, D, JK, toggle, and many more. Why do we use flip-flops in automating memory? They offer us high speed, therefore immediate read and write responses. They are reliable, they are easy to implement in digital circuits and control logics, therefore they are simple. They offer us low latencies by providing us immediate response, which is crucial for safety and critical features. They have stable state retention, therefore they can hold data securely without frequent refreshing. They work well with clock systems for precise timing, therefore they are synchronized, and they are used and they are ideal for storing control states and small bits of data, therefore they are compact and small data. The adaptive headlight system works on sensors and flip-flop memory. LDR, radar, steering, angle, aim, speed, ambient light sensors collect real-time data from the surroundings, and flip-flop memory stores the important information using the flip-flops. Controller unit uses this data to decide when and how to adjust the headlights. Actuators change the headlight position and brightness automatically, and the benefit of this is that flip-flop keeps the last known headlight state, helping the smooth transition. This ensures the headlights respond instantly, correctly, and even after power loss. Role of memory in adaptive headlights. They store input data states, they store decisions, they store configurations, and overall, the functionality enhances system responsiveness, consistency, and customization for safety driving. D flip-flops are the preferred choice for our project because D flip-flops have a single data input along with clock input, which is a pretty straightforward design that makes it easier for us to understand and implement this logic in digital circuits. They have direct data storage and minimal control logics because D flip-flops are simple and they reduce the need for any additional control logic, streamlining the circuit designs and reducing potential points of failure. D flip-flop catches the input data, maintains the stable output until the next clock edge, ensuring consistent behavior in the system. D flip-flops are noise immunity. D flip-flops have noise immunity, and they have predictable timing. Memory cell architecture using flip-flops. D flip-flop array organized to store parameters like headlight mode, steering angle, and speed thresholds. Control signals. Control signals consist of clock signals, writing enable, and reading enable. Writing enable activates writing new configurations for the states. Reading enable activates the reading current states. We activate the writing or reading mode and then set data inputs or apply the clock pulse. We apply clock pulse to store data and read data to adjust the headlights. Storing of sensor data. Latching sensor data consists of latching the ambient light sensor data, steering angle sensor, and speed sensors. The main function of this is to store the external light intensity, detecting steering wheel angle for headlight direction, and speed sensor to store and monitor the vehicle speed. The control logic of flip-flops is to provide stable output that can be used for decision making in real-time applications. And microcontrollers read the data from flip-flops and perform computations and send the control signals to actuators. The data flow consists of flip-flops latching sensor data, which microcontroller reads at the specific interval of time. A microcontroller uses the latch data to make decisions, for example, adjusting headlights based on ambient light, steering angle, and speed of the vehicle. The clock signal synchronizes the operations of flip-flop and microcontroller, ensuring easy data handling and timely responses. State retention for decision making. In adaptive headlight systems, several operations need to be retained. For example, concerning states, they typically indicate that the headlights are adjusting based on the steering input of environmental conditions. Straight state. This represents the normal operation when driving straight and there is no need for changing the beam light. The other possible state might consist of turning right, turning left, cornering, etc. The timing considerations consist of clock synchronization. We ensure all the flip-flops update simultaneously using a common clock. This prevents unstable states where data crosses the clock domains. Data must be stable before the clock ends. On violation of this condition, wrong data capture and unstable states will occur. Data must remain stable after the clock age. On violation of this condition, data corruption due to premature inputs occur. The model that we are discussing here is power efficient. Adaptive headlights must always be ready, but not drain the battery. D flip-flop based retention ensures safe and lower power operation without losing the states. Therefore, we get near zero power consumption when headlights are adjusting and an instant wake up from idle when steering input changes. The main components of the real-time systems of adaptive headlights are microcontrollers, 8-bit memory, and sensor inputs. Microcontroller can be considered as the central processing unit that will read data from the memory and make its decisions. The storage unit will retain sensor data and control states of the headlights. Various sensors that provide real-time data into the system will be taken from sensor inputs. Use cases of this scenario are that microcontroller captures data from sensors, stores it into an 8-bit memory, then it will retrieve the stored data, make decisions about headlight adjustments, and based on the retrieved data, the system adjusts its headlights, positions, and intensities. There are a certain design constraints to this system, aside from all the upsides. Flip-flops are area intensive, and especially while storing multiple bits, suitable for small memory that is not for large data storage. Flip-flops offer very low latency, ideal for the real-time systems like adaptive headlights. Data can be written and read with a single clock cycle, ensuring immediate response. Critical for dynamic adjustments when vehicle speed or direction changes rapidly. Flip-flops consume low static power but may consume a very high dynamic power using frequent switching, efficient for short-term memory, especially when paired with clock gating techniques. It is important in automotive systems to maintain energy and efficiency and battery life. Flip-flops are relatively robust and stable under environmental stress. Here's an example of how flip-flop is used in adaptive headlight systems. The flip-flop will store the sensor data or control flags like whether the vehicle is turning left, if the high beams are on, or if the car is in low visibility mode. These small pieces of information stored as bits are essential. They feed directly to the control logic that decides how the headlights respond in the immediate real time, like adjusting the beam angle or brightness or improving visibility and safety. To conclude this presentation, we explored the design and implementation of a flip-flop based memory system which was tailored for adaptive headlight control in vehicles. Throughout this presentation, we've seen how this memory system serves as a reliable and efficient solution for storing headlight positions and adapting to various driving conditions in real time. By leveraging this predictable and low power behavior of flip-flops, we ensured fast data retrieval and minimal latency, both crucial for automotive applications. We also demonstrated how memory system integrates into a larger digital logical circuit, allowing dynamic and responsive headlight adjustments based on environmental inputs like light intensity and obstacle detection. Our simulation and hardware implementation validated the design, showing consistent performance under various test case scenarios. This not only confirms the viability of flip-flop based memories in such control systems, but also opens the door for further enhancement in smart vehicle technologies. The references for this presentation were taken from electronics tutorials. all about circuits, microchip technology, and understanding the information. We use black box AI to boil down the information that was taken from our textbooks, Digital Design by Maurice Mano, Fundamental Digital Circuit by A. Anand Kumar, and Digital Circuits and Practical Approach with VHDL by William Clydes. Thank you for all your time and attention. I hope this presentation gave you a clear understanding of how flip-flop based memory plays a vital role in adaptive headlight systems. From storing sensor states, enabling smart light adjustments, these tiny circuits help drive big improvements in our automotive safety and user experience.